All right, what's going on, guys? Welcome to Gary's Ground School. Today we are going to be talking about instruments and how they work, their errors, and whatnot. Once again, timestamps in the description if you want to skip ahead to some points that you don't really understand. This is just a brief overview of everything that you need to know. Very first thing we need to know is your equipment required for IFR flights. You got to add, of course, the 8 tomato flames and the flaps, or your VFR and night VFR equipment, and then you add this on top. Really great acronym, something you need for IFR flight, of course, GRABCARD. Generator or alternator, radios, communication and navigation, appropriate to the navigation you need for the route. Altimeter, which must be sensitive, must have that Colesman window. Your ball, also known as an inclinometer, which can be found down here. That's your inclinometer right there. On your turn coordinator, a clock with it has to have a second sweeping hand, or digital, presentation. Attitude indicator, which is right here. Rate of turn indicator, which is right here. And your direction indicator, which is down here. So next is your glass cockpit or primary flight display, which is down here. And it says, do glass cockpits have the same equipment / instruments? They do. They get you their data in a different way, but they have everything you need for an IFR flight. Right here is your airspeed indicator. This is your altimeter. This is your VSI. Of course, it's straight and level, so it's not reading anything. Right here, this is your ball, more or less, or your inclinometer. This shows you your angle of bank. This right here is your HSI, or your direction indicator. This is your attitude indicator, and that's pretty much everything you need for an IFR flight. Remember GRABCARD though, that is the big thing to remember. And next we have which instruments are traditionally gyroscopic. Big word, traditionally, because nowadays you're getting your data from your air data computer or attitude heading reference system. But back in the day, your gyroscopic instruments were powered by a vacuum driven engine pump, which is your attitude indicator, your direction indicator, and your turn coordinator. Your turn coordinator is actually gyroscopic, but it is electrically powered instead of vacuum powered. Next, we have what are the principles of a gyroscope. So two main are precession and rigidity in space. So imagine these, you see these little spokes right here. Imagine they are actually attached like firmly to the aircraft. As the aircraft moves around this gyroscope right here, which is spinning rapidly, which is why it is rigid in space, that is going to give you, whatever you need it to give you. It's just not going to move. And that is what's so crucial, because there used to be this thing called seat of the pants flying, which a lot of pilots did, and a lot of pilots died because of that, because you don't know where you are. That's why the last unit I covered about spatial disorientation, that's why gyroscopes are so important to maintaining that orientation. And gyroscope is mounted on gimbals, which I just showed you, which are the things that freely rotate around your gyroscope. So next we have precession. I just discussed rigidity in space. Precession is more or less as you apply a force to a rapidly spinning gyro, that force is going to result 90 degrees later. And actually go on Vsauce and look up gyroscopes, because Vsauce gives you a great example. And I know like Vsauce is like a meme channel, but it's a really good example of how they work. It discusses precession and rigidity in space. The next we have is the attitude indicator. So actually on an attitude indicator, you see these fins right here. These fins do not move at all. What actually moves is the artificial horizon in the background, which as you pitch up or down, that's going to make the artificial horizon move down or up. And then you got this ball down here. So when you start your aircraft up, you want to set these fins to the artificial horizon. You want to make sure after 5 minutes, after the vacuum has enough power, after it's rotating fast enough, that is correct and stable. If it's not, you might have a big problem on your hand. This, of course, is a schematic of how it all works. It's really cool to look at if you want to, but that's just the general principle. Next, we have how do we adjust the attitude indicator before flight? I literally just went over that. It's by this little knob right here, and you adjust the little plane up or down. Of course, in a PFD or a glass cockpit, you don't get that privilege because it automatically does it for you. But if you ever fly steam, which is what I learned on, that is something you need to do. So there you go. Next we have, when does the attitude indicator have the greatest errors in a turn? So whenever you turn a full 180 degrees, that is when your greatest error occurs. So just think about it. east to west, you turn that much, and that's going to make your attitude indicator precess, which if we go over here, imagine you are turning to the left, like a steep turn to the left, and you come out of that turn, your attitude indicator, the gyros inside of it are going to want to precess, and it might show you a slight indication to the right. Now in VFR, this is no issue, but in IFR, it can lead to some moderately severe, that's an oxymoron, disorientation. But just remember, if you're coming out a turn from the left, a straight and level flight, you might get a turn in the opposite direction. And that's one thing on your written that you'll have to know. And it's one thing to know in flight because it can lead to spatial disorientation, which we don't really like. The next is tumbling. Now, you won't really experience this in electronic, PFD, glass cockpit stuff. But however, back in the day with aerobatic planes, or if you're just somehow gotten upset your plane so much, not emotionally, of course, just like stalled or whatever. If you exceed 100% of bank or 60% of pitch, so 60% up and down, 100% left or right, it's going to tumble your instrument because the gyroscope is going to precess so much that it just interrupts the whole flow of things, going to tumble, and this is what it might look like. Now, after a while, they will come back straight and level. It will catch up with itself and it will stabilize, but sometimes they will not, which is why it is incredibly important to know this. That is why a lot of them have cages, which will cage the gyro so it cannot move, which means it cannot tumble. Heading indicators are, once again, vacuum powered. They use a different form or a different way of using the gyroscope as seen in the schematic to give you your heading. And the thing is, this you have to set every time before a flight, unless of course it is electrically powered, getting magnetic direction from another source. But 9 times out of 10, if you're training in a steam, like somewhere up in the cockpit, there's going to be a magnetic compass, which you'll see later in these slides, where you set that and align it to. Because 9 times out of 10 times, when you start the aircraft, it is not going to be aligned with your magnetic compass, and your magnetic compass tells all. As you can see later, it just has a lot of errors involved with it. The next thing to discuss is your horizontal situation indicator. What it basically is a heading indicator plus a VOR display. You see right here, this is your CDI, this is your CDI and a VOR indicator, and this is your CDI here. And as you can tell, this compass card, you cannot move it. It automatically gives you your heading, which will lead to really good spatial orientation, because this, you can have your OBS set to a completely different radial, the radial you're trying to pick up from the VOR while you're facing a complete opposite direction here. This really makes it simplified. You would just fly towards that little CDI right here, to and from flag, here, to and from flag. And you'll see these arrows here, and this makes it so much easier. I grew up on this and this, but a lot of people nowadays are using the HSI, which I love, makes everything a whole lot easier. It leads to better spatial orientation. The next are turns, and this is more of airplane, aerodynamic theory, whatever. What causes an airplane to turn? You'll be like, oh, just left aileron, right aileron, there you go, it's going to turn. But more specifically, this radial right here is your horizontal lift component, and this is your vertical. It doesn't show it in here, but your vertical component decreases as you turn, and your horizontal component increases. And how you increase your vertical component of lift is by pulling back on the yoke, which is going to give you up elevator, and increase your vertical component of lift, which is why in steep turns you need so much back elevator. Sorry, I didn't mean up elevator, back elevator to maintain a level flight. So here's the thing, in IFR, how do we know when our turn is coordinated? As you can see down here, here's a turn coordinator, which will probably give you your turn coordination. You also have a slip and skid indicator, which is usually in the older planes, but you might see one day flying some general aviation aircraft. The main difference, though, is your turn and slip indicator only gives you your rate of turn and your quality of the turn, while your turn coordinator gives you rate and roll. You can see by the aircraft, it's banking to the left, while this is just a needle indicating rate of turn. However, this only indicates initially rate of bank until it is established. What primarily gives you your bank angle is your attitude indicator, but that's just getting into primary and secondary instrument theory, which we will learn in a later lesson, hopefully. The next thing is, what could you use as a backup for the attitude indicator? And I actually just said this, So this, like I said, indirectly indicates your bank for your turns, and of course indicates rate of roll, which more or less could serve as a backup for the attitude indicator. It just does not show pitch. That's why the attitude indicator shows. But for pitch, you can use airspeed, you can use your altimeter, and lastly, you can use your VSI for pitch. The next thing we do is estimating the angle of bank required to make a standard rate turn. 9 times out of 10 for the aircraft you fly in, like it's from 90 to 130 knots, which how you get the angle required is you divide true airspeed by 10 and then add 5. So let's say you're flying at 100 knots, that's easy. Divided by 10 equals 10 plus 5, 15 degrees. So if you look right here, if you're like training in like a DA-20 or a Piper Archer, Piper Arrow, your standard rate's usually going to be right here. Right, 15 degrees because this is 10, 20, 30, 15 degrees right there. During a constant bank level turn, an increase in airspeed results in a decreased rate of turn and increased turn radius. Next, what we got is our slip and skid. Basically, I could go into horizontal versus centrifugal force, but right here, a slip is a rate of turn which is too slow for the bank, and the ball moves to the inside of the turn. So if you look down here, the ball is still left on the inside of the turn since we're banking to the left, giving us a slip. A skid is a rate of turn that is too great for the angle of bank, and the ball moves to the outside of the turn. And if we look right here, the ball is on the outside of the turn, we're turning to the right, skidding the aircraft. Think of this one as the aircraft falling to the ground, like the ball is pulling the aircraft to the ground, and this as the ball is pulling the aircraft outside of the turn. As you can see down here, as I was saying about horizontal component of lift and centrifugal force, a slip, see the ball how it's inside the turn, a slip, your horizontal component of lift going this way is actually greater than your centrifugal force. Your centrifugal force, once again, like when you have a pendulum or something swinging around, that ball just wants to shoot in a straight direction out away from the circle. However, in an airplane, you can't shoot straight out because you have the factors of airspeed, resisting and pushing and lifting and whatnot. Right here, you have a slip, which is your centrifugal force is greater than your horizontal component of lift, causing your aircraft to feel like you're getting pushed out of the turn. And then, of course, a good quality coordinated turn is when centrifugal force and horizontal component of lift are equal. Keep in mind that your vertical component of lift, might not equal horizontal component of lift, but you can still have a coordinated turn. The next is magnetic compass, which some planes nowadays don't even have because it's all electronic, magnometer, but they have so many errors. You have variation, which is the angular difference between the north and magnetic pole. And if you see here, these are your magnetic variation lines. So what does that mean? So true north is from the North Pole, but your magnetic north is actually further south than the North Pole, which let's say you were over here, that is going to cause, let's say I'm pointing to magnetic north, which I'm very off, I know, but let's say I'm pointing towards magnetic north, and then if you point to true north, it's going to give you an angle that is much different. And that's why we have these angles during flight planning, so we know what direction we are actually going. Next, we have deviation. Errors due to magnetic interference with the metal components of the aircraft. Just think of it, if you take a piece of metal and put it close to like a handheld compass, that needle is going to start, like freaking out, which is why a magnetic deviation card is required in the aircraft. You see right here, let's say I was on a heading of 150. I'm actually on a heading of 152 magnetically. And the last error we have is the magnetic dip, which as you're flying over the earth, let's say I was flying right here, my magnetic compass isn't pulling out here, it's actually pulling towards the earth, which is going to cause you that dip, which as we move on right here, it's going to cause our errors. While I could read all of this, all you have to know is UNOS, undershoot north, overshoot south, which means if I was going to turn to the left from a northern heading, I would initially indicate a turn to the right. And if I was to turn to the left from a southern heading, it would actually overshoot that by a large margin. So the next we have, I could once again read all this, accelerate north, decelerate south. The most stable directions to turn for the magnetic compass is from an east or west heading, but due to the magnetic dip characteristic, we have accelerate north and decelerate south. And so if I was to accelerate to the east or to the west, my compass would dip to the north, and if I was to decelerate, it would naturally inversely dip to the south. So next, what are our pitot-static instruments? Our vertical speed indicator right here, altimeter, and then finally your airspeed indicator, which are our main instruments given by our pitot-static system. Here's a regulation you have to know. How recently does the altimeter system test and inspection need to be done for IFR flight? That is done every 24 months. That is very crucial, or you cannot go on an IFR flight. The next we have, how does the airspeed indicator work? And this is something I didn't learn until the beginning of instrument training. You have ram air pressure coming in, right, which is received right here by the airspeed indicator, and you also have your static air line coming in. And of course, static air is just undisturbed what the air pressure is reading. So if you have undisturbed air coming in and ram air pressure coming in, that's going to cause a difference, which I believe is called dynamic pressure, which correlates to airspeed. So just remember, it is the difference between your ram air pressure and your static air line. Next, we have types of airspeeds. The first is indicated airspeed, which is read directly from the altimeter. We have calibrated airspeed, which is indicated airspeed corrected for instrument error. And if you look down here, you have wind coming into the pitot tube, directly, and it's doing fine and dandy. But if you go down here, the pitot tube is at an angle, causing the wind to enter at an angle, causing a different airspeed to be read than if it was straight level, which is an instrument error. Equivalent airspeed is calibrated airspeed corrected for compressibility factor. You're like, yo, what's compressibility factor? It's pretty much, as very fast aircraft, it rarely ever applies to general aviation because our aircraft are so slow. But let's say for jets, as the airspeed goes around the nose of the plane, it's going to be displaced so fast and so greatly, it's going to cause the air to bunch up, much more pressure, shoot off, and give you a different reading on your pitot tube on your wing. So once again, CAS, corrected for compressibility factor, the air around your nose is going to be a lot more compressed than the air around your wings. Next is true airspeed, speed of the aircraft relative to the air it is flying through. On a perfectly calm day, your true airspeed is going to match your ground speed, which is just an easy way to think of it. Ground speed, of course, is your aircraft speed going over the ground, much like your car, for example, always reads in ground speed. Last thing we have that's kind of trivial, because we may never see this in our flight careers, but you might if you decide to fly really fast things, is the Mach meter, which is just simply the ratio of true airspeed to Mach. Next, and this is more important for your altimeter, is standard temperature and pressure at sea level. As you can see at 0, this is standardized. It's not like some, set in stone, like 2 + 2 = 4. It's just what we said it was going to be, so we could have something to work off of, as a society. At international standard atmospheric pressure, altitude 0 feet, pressure is 29.92 at 0 feet, temperature is 15 degrees Celsius. And what's cool is around 18,000 feet, your atmospheric pressure is actually going to be around about 50%. And as you can see in the standard atmospheric model, 18,000 is around half of what 0 feet is. Next, we have our altimeter, which our altimeter just reads from the static port. It does not really need the ram air input or the drain hole to be operative. It's just reading from the static port, measuring the difference between barometric pressure. As the barometric pressure decreases and increases, your aneroid wafers are going to, detect that, giving you an altimeter setting. Next are types of altitude. We have indicated pressure, density, true, and absolute. Indicated altitude is what's read off the altimeter, much like your indicated airspeed is read straight off the airspeed. Pressure altitude is what the altitude is when it's set to 29.92. So pressure altitude is more or less the altitude above the standard datum plane, which is what the standard atmospheric model is based off of. Density is density altitude, pressure altitude corrected for non-standard temperature. This is going to give you your climb rates, very important in your performance charts found in your POH, for example. True altitude is the actual height of an object above mean sea level, while absolute is the actual height of the aircraft above the Earth's surface. As you can see here, absolute terrain, true altitude sea level, pressure altitude standard datum plane, and then of course your indicated is read off the altimeter. So what are flight levels and where are they used? Flight levels can start anywhere from 4,000 feet above, typically. So like 4,000 feet is flight level 040. However, with the altimeter, you might have it set to 30.12 on the altimeter setting, but right when you cross 18,000 feet, that's when pressure altitude flight levels start. So right when you cross 18,000 feet, you would set your altimeter to 29.92, and you would read the altimeter from there and keep climbing until you reach your designated altitude. So the next big thing about an altimeter that you need to know is when flying from hot to cold or high pressure to low pressure, your altimeter will read too high if you don't adjust it. For example, here, from warmer to colder temperature, you're actually descending, but your altimeter is slowly adjusting and indicating the same exact altitude. And of course, this is a perfect example of it doing that. Usually it's gonna be a little different than that, but high to low, look out below. The next is your vertical speed indicator. Main thing you got to know about this, it has a massive delay, so it's not going to show you per millisecond what your rate of climb or rate of descent is, but that's the main thing. All it really reads is rate of climb and rate of descent. Next, we have our pitot-static system errors, which are very crucial because they can be caused by the blockage of the pitot tube, static port, or both. But main thing you got to be worried about is your pitot-static port can actually clog, usually due to dirt or whatever. But if you're flying into icing conditions, 9 times out of 10 it's going to ice there because usually small protrusions freeze first. Here's the thing, what would you suspect if your airspeed indicator indicates 0 in flight? If your airspeed indicator is indicating 0, that means that your ram air inlet is clogged, but your drain hole stays open. On the other hand, if your drain hole and ram air inlet were both clogged, your airspeed is going to remain in the same place, and as you climb and descend, and as your static port gets more and less pressure, your airspeed is actually going to act as an altimeter and climb. As you climb, it's going to slowly get faster, and as you descend, it will slowly get slower, quote unquote, which can really mess you up if you're not aware of it in IMC, because as you know, when you pitch down, your airspeed naturally wants to rise. Next you have is static blockage. If your static port is blocked, your VSI will actually drop to 0 because there's no difference in pressure anymore, which will, of course, cause your altimeter to freeze. And you might say, well, all hope's lost. If my static port is frozen, I don't know what my altimeter is. But last resort, you can break your VSI. Usually aircraft have alternate static sources that you can pull out. Breaking your VSI will open up that static port, considering aircraft is not pressurized, because then there would be no point at all. But if you're flying like a PFD or a glass cockpit, you don't want to break that glass cockpit. They're definitely going to have an alternate static port in that case, but some older aircraft don't. So the last thing we have is if an alternate source of static pressure is used, you just got to know what's going to happen. Let's say you break that VSI face or you pull that static pressure. It's actually the altimeter will read a little higher. The airspeed may read a little faster, and your vertical speed will momentarily show a climb. Keyword momentarily, and that's what will ask you about. But yeah, that's it. Thank you for watching. If I got anything wrong, of course, leave the comments. And yeah, hope you all take care.